So I'll introduce you to a man with a Mac that seems to work. Over to Chris. Thank you.
Thank you. So today I have two presentations. The first thing I wanted to say is that I've had some feedback from yesterday. All the GNU Radio files and companion files I've put on my 2E0OBC website. You should just be able to Google my call sign. It will come up, and you can download the GNU Radio charts that I've been using on there. But today, one of the things that I've been asked to do is to give an update on Martin and my director, Guglielmo Aglietti's behalf. And there's two missions that I wanted to talk to you about. The first is one called Remove Debris, which is about active removal of objects in space and the technologies that go on in, on and around it. The other one is called ALSAT Nano, which is a joint educational CubeSat mission between the Algerian Space Agency and the UK Space Agency to fly UK payloads. So kind of got two things, I've got two for here. So the actual, what we call active debris removal, or ADR, is the sort of missions that we need to start to think about with a lot of the current issues that we're starting to find in space. And really one of the things that we need to do is actually start to de-risk and mature a lot of these technologies. So whether it be understanding how they are, how objects move, and actually being able to approach and capture different types of objects. And we were awarded an FP7 project for 13 million euros, and it has 9 partners, over 60 staff, a big long 3-year duration that started in late 2013 to early 2017, when we should actually be demonstrating some of the technologies. And the things that we wanted to talk to you about is really our net and harpoon pieces that we've been working on, the deorbiting technologies, so drag sailing, and what proximity operation technologies are needed, in particular in vision and LiDAR navigation. So there's a lot to kind of pack in there, okay, of the technologies that we've been studying and looking at. And of course, I talk on behalf of actually a lot of the different partners here, so apologies to those if it's not as accurate as they would like it to be for this particular audience. The key thing that we'll be doing is launching a microsat, and it has a chaser, and it has 2 target CubeSats that we'll be pushing out, essentially out the side of our microsat. So, like I said, we have an absolute swathe of partners, ranging from Airbus, SSTL, from ISIS, our colleagues that are here today, and as well as a lot of the guys that we know and love, obviously, at the Space Centre. But each of these partners has some very, very particular jobs. In particular, the university itself, SSC, is doing all the project management, bringing the team together, and the design of the payloads, the drag sails, the harpoon structures themselves. SSTL, obviously with their competencies in microsats, are the platform provider, okay, and the actual operations systems. Airbus, at various different locations, are producing the nets, some of the vision navigation system, and actually the harpoon itself. So they're kind of covering a lot of those active debris removal technologies, and we are providing the fodder, so to speak. ISIS are working on the deployers with us, and then there are various other small SMEs around that are helping us with other parts of the program. For instance, visual-based navigation algorithms themselves, how we go about taking those systems forward. And the best way to really describe that is to sort of start off with a video that we generated for the Royal Society show, which will actually detail, hopefully, a bit more about what the mission is about. So, he says they should be sound. So that is really just to give you a flavour of the concept of really what remove debris is, and some of the key technologies that we need to actually start to address in active debris removal. As suggested there, there's obviously my director, Professor Guillaume Aglietti, should you want to contact a bit more further. And there was lots of kind of things that were packed into that video, and the sort of ideas that and things that we need to be able to achieve to make sure that we are responsible in our use in space. And I wanted to talk to you a bit more about exactly what will actually be occurring. We would actually be hopefully going up with an ISS with launch and preparations on there, and after deploying from the ISS we can start to commission things. And this is where the ordering of your payload starts to become important. Working out what we would do on our net demo, our visual-based navigation demo, our harpoon, and our drag sail. So of course that is a sort of order in which you want to perhaps address risks in a mission as to whether or not you want to try your deployables first, whether or not you want to try different things first, and all of those different pieces of ordering. But it would be quite a very short duration mission, not even lasting kind of a year and a half is what is planned. The launch itself process is by ISS, visiting the vehicle, performing transported to get us unpacked, goes into the Japanese module, goes onto the Kibo arm, goes through the airlock, releases the platform. Everyone has kind of seen those very, very beautiful videos of how they're actually releasing those pieces. But it does mean that then that we're restricted to 400 kilometer sort of orbits at 51.6 degrees inclination. Now, that is particularly important because it starts to have ramifications on what your lighting conditions are going to be. So if you're trying to assess and view an object, what exactly that is going to occur. Obviously, it has issues as well with your power budgets and your communications too. So even though that it's from the ISS, those challenges can still be overcome through the analysis that the teams are doing. So the payloads themselves, the net demonstration system, you can see kind of a couple of CAD models here. They've been testing the deployments in drop towers of how the net would operate, how it would actually come out of these different systems, and then how it would then perhaps go through and capture things. And they've been testing those things in parabolic flights. And you can kind of see the release of a CubeSat. We actually have an inflatable on there that the Space Centre's been developing, where the net would then be released and hopefully captures for deployment down to Earth. Now there's a video that I wanted to show you, which is how they were doing these sort of drop tests, how the net would come out. And of course all of this sort of information is critically important to understand how these dynamics are going to work in space. We've not necessarily understood fully all of those different pieces, and this is really where the R&D comes into it. How is the net going to come out? What sort of are those vectors that we're going to need to start to challenge and actually capture all these different pieces? So that work is well underway. The next piece is the visual-based navigation system, and it is not a typical LiDAR that you would come to know and love, where it be one of the Connect ones is actually quite a precise piece of measurement equipment, but it also has some receivers and transmitters on there as well, so you've actually got points of reference as well. It's kind of not cheating, so to speak, but we need to have something going between one of the CubeSats together with standard camera technologies and LiDAR technologies to actually start to understand, is this working the way we expect? Do we appreciate and understand all of these different pieces when we try and do these things? And at what ranges do we start to then lose these systems? The harpoon itself will probably not shock you that we couldn't actually just release a CubeSat and then shoot a harpoon into that, because if you miss, then you've got essentially a massive spear/trident object thing traveling around Earth. Agencies don't, or not enamoured to that kind of idea, so we have to shoot it into a plate to make sure that obviously the spear of death doesn't just spiral around Earth for a long period of time. The harpoon sort of target assembly itself is again another precise instrument. There's a deployment direction coming out, and we have our own mechanisms as there to pull things back in. And they've tested a whole bunch of evolution of projectiles that you can see in the corner here. Again, this is the sort of work that is undergoing extreme research because they're doing these things for the very, very first time. And last but not least, there's the drag sail implementations, which is actually a 9 meter square, approximately, sail. There's no need to control that, as the demonstration actually it's kind of off the front, and it has a centre of gravity front, allowing for your aero pressure centre, which means it will be quite stable. It's based on inflate sail, but essentially a payload version of that same piece, and you can kind of see it down here. And actually, we've got a deployment video that I can show you as well. So this is one that we've showed at conferences before, but it goes to show kind of, you've got this sort of piece coming off the side here, which is where it kind of comes off, and then you've got the actual sail coming out in the middle. So it's all of those motors, all of those pieces to understand how these things are going to fit together. Fast forward a bit, it takes us a long, long time. It takes even longer to put it back together, I can assure you. But if I skip forward, you kind of get the idea. So we've got a sort of a big table that we've been having in our lab just to show what it happens. So you can see the CubeSat up here, the booms. Yeah, it's very, very, very controlled deployment to make sure that it works. So the platform itself is designed by SSTO, and it actually looks like a more regular sort of SSTO sort of 100 system. Has a net function in the middle, and we have certainly different assemblies and facets all to put all of our pieces on one side. You'll have your typical sort of cameras, communication systems on the side, but you're going to want to have one front which is doing all the main business of our mission. The rest of the satellite itself looks moderately vanilla for microsat standards, with sun sensors, GPS receivers, magnetalkers, as well, monopoles, antennas, reaction wheels, etc. All of the things that you would come to kind of love and expect from a mission of that class. The CubeSats themselves are developed at Surrey, and we call them well, kind of debris sats or DSATs, and some of them are active and some of them are passive. So semi-active ones, they've got an onboard computer, power, and obviously the inflatable structure. We've been testing it over in our labs, and it has an internal sort of release mechanism, sort of a controlled gas cylinder system in there. And of course we have to undergo our own very strict rules to get that onto the ISS as well. We have to undergo even more things as soon as that launch became appropriate. So again, it's all qualifying of technologies that are useful for future. The other target as well is DSAT-2, which is actually fully active. It's got OBC power, AOCS, and an inter-satellite link, and that's obviously the one for the visual-based navigation. So they can actually work on that, and they'll have a typical avionics core, and it's undergone vibration testing. That's the state that we're in kind of now. And really, I've got to burst through that at lightning speed, really, because we're currently in the final design and preparation of the flight models for the end of the year. We've launched early next year, or currently that is what we are rostered as. But the key thing is obviously that this can be really valuable to the community. Learn from the papers that we'll publish, learn from the press that will come out of these things to understand whether or not these opportunities actually work for doing in-orbit demonstration of active debris removal. The next step from that is to then see how we can take those things further. What are the computing requirements, what are the attitude, orbit requirements that we need? So starting with a small sat platform is a good way to go. And obviously, because CubeSat's a low-cost technology, and we've got experience in building those, we can then use those pieces as well to actually try something that everyone has really necessarily done. So, likely to be the world's first active debris demonstration machine using artificial targets. Please save the Q&A to the end, because actually now I need to tell you about a CubeSat mission. So I'll close this guy down. Don't need that. And I'll find my AMSAT presentation. So now something slightly more different, in the fact that I've been working together with a massive team at the SSE, UKSA, the Algerian Space Agency, and UK payload teams in building together this 3U CubeSat, which is between the UK Space Agency, SSE, and the Algerian Space Agency, or ASAL as we call them. And I wanted to kind of give you an overview of what this is doing, and actually how you could then perhaps be involved by picking up our beacon. So just as an overview of where it all came from, March 2014, really the specific action there was to do a joint CubeSat activity to make sure that it can help and design and deliver education to Algerian students. So we've had their MSc students over in our classes. We've got 2, 3, perhaps even 4 PhD students. I have 2 PhD students from Algeria that are working on research in these areas. One, in fact, on debris removal, communications, and navigation. And the UK is kind of responsible for building that. And what we did is we want to obviously strengthen our international ties with people, with other sort of emerging space and aero nations. And we obviously wanted to offer flight opportunities, much like UCube did on the behalf of UK Space Agency. So in 2014, this is really where the bulk of my work was done on the preliminary design, so all of the initial CAD design work, and actually the room and space that you would need for payloads. So we kind of tried to be as flexible as we could by going, here, there's a volume here, we'll try and see what we get and put in as much as we possibly can. And we sort of started to develop, obviously, all the interface requirements. So this sort of bottom stack here is ADCS, payload interfacing, comms, and power. And what we eventually did is we had a sort of announcement of opportunity, and we selected 3 payloads in March. And they are the E2V camera, so C3D2, which is a follow-on from UCube's C3D1, I guess. The Space Mag PV boom and the thin film solar cell. The boom itself is from Oxford Space Systems, and the thin film solar cell is from a Welsh university, Glenmuir, he says. So the C3D2 has 2 wide field images and 1 narrow field one, with the wide field imager focusing on our boom payload, which is from Oxford Space Systems. So there's an opportunity there for us to take a picture of the boom to actually then get a visual representation of what's actually happening with the system. It's obviously a pilot one, and they want to then use the data that they can hopefully collect to then get back imaging things for working with their students at university with the OU. Yeah, so do apologise. The boom itself, the correct name is the Astro 2 boom, because it got slightly de-scoped. But the retractable boom payload is a proprietary, as it says there, carbon fibre, comes out to just over 1.5 metres, and actually incorporates RAD-FETs as well. And what you can see here is it's got some stacked electronics, some motor systems and configurations and stops, and then this is kind of a boom plate which comes kind of out the side, and it's got a mounting bracket. So it's just trying to assess all those things and get them done in quite a quick and accessible way. The thin film solar cell is, again, based on a new technology which is really thin and kind of flexible, and we want to see how they degrade over time. So we want to check their voltages, their currents, assess them over time to understand what degradation effects can happen. But really the focus of this is, after we've kind of selected the payload, SSC did a lot of work in making sure that we can fit all these pieces together, is on the focus of the Algerian students themselves. This is Yasser and Majid. These are 2 of our PhD students. Yasser itself working on multi-core compilers with myself, and Majid working with Professor Underwood on magnetic control of cubesats and some of the problems that we have in rotation and spin. But you can kind of see some of the other Algerian staff that have come with us when we've been testing our SQM. So we built up an SQM model and engineering models to kind of go through almost the full process with the Algerians of a space mission. Let me just move those so you can see the text. Yeah, so you've got the vibration there, you've got the bottom there, and that's sort of then with one of the EMs that we've built. So, fast forwarding that, okay, this is kind of what the CubeSat looks like roughly inside. It's always very, very nice when these things come together as planned in the CAD models, and it starts to become real. You can see we've got a kind of bottom stack like we had before, which contains a newer version of the transceiver, a magnetometer at the bottom, the Stellenbosch ESL ADCS stack, Clyde Space Power System, a Surrey switchboard, and then we've got all of our payloads, the OSS boom, the thin film solar cell, and the C3D2 camera. And you can kind of see in this picture here kind of how far the boom kind of extends out, and we're quite interested to know what that's going to happen to the dynamics of the spacecraft. They're very interested to know that the technology can work reliably, so they can actually go ahead and do things on other missions. Fast forwarding again, we've recently just had our FRR, and you can see the spacecraft just in the background there. There's a lot of shots that I kind of have with launch sites, and I'm sure ISIS do too, where they've got this massive payload on thing, and right in the back in the corner there's like a tiny 3U or 1U CubeSat in the corner, which usually just is a couple of pixels in the end. in a lot of the photos. But the main guys obviously that worked on it, we've had a sort of a management board that has been working with us, a big sort of, software team to progress what we've been doing, as well as the UK Space Agency themselves. So, FR passed, DDR passed, all of these things. But the ground station itself is something that's slightly different in this configuration. This is an Algerian mission, and as such it needs to be operated under UK law from Algeria. And what we've been working together with is understanding how that's going to fit together, so that we can understand really how these operations are going to work. So I've been out in Algeria and we've been helping them build their own VHF UHF ground station. This is the picture of it down here. Again, always nice to go from CAD models all the way up through to these things. And the guys in Algeria have worked really hard to kind of make that happen with, with just some guidance from SSC. And the idea will be is that obviously they want to be transmitting up from ASAL, and we can receive and support from SSC. What we've been developing kind of on the side of that is our mission control software, which is based on databases, regular databases, and web PHP user interfaces. We use Python for the back end and all the hardware control from the radios, the TNCs, and rotators, and we pass script everything. So we understand what we want to do before passes. We've been training the operators to understand this tool so that they know what to kind of expect for each particular orbit. What's really great as well is it's been a logger of everything since sort of early this year, and it can then chuck out all the statistics of actually how much testing has gone on this spacecraft. Oh, don't know where that came from. The ground station MCS itself is kind of broken down into a whole bunch of tabs. So this is kind of the interface that users in Algeria will be using. And you can kind of see it's just a web page, but it allows them to control different things like the uplink, the downlink, and schedule perhaps what passes you might be looking at in your system. So they spent a lot of time and effort in making sure that the software matches with the ground station systems, and that actually if they need to use things, they can do and do it in an easy and accessible way. The main mission control panel, they can add tasks and send telecommands just through some simple click buttons, and they can generate then a series of scripts. So if you wanted to then go, okay, we want to turn on a payload, well, first we need to check our battery health. We will want to check then our current and timeout limits. We will want to check all of these things need to be validated and ensured before you then go ahead, switch something on. When you do that, how did it behave? All of the sort of critical things just to understand in quite a slow and easy way how you would bring something up. So that all these tools are really great, and the guys have done a fantastic job, and it's certainly impressed me on understanding how these things are put together. What's great as well is that we can then use, again, some fairly useful tools to then start to chart and understand really how the satellite's performing. How do you know what values you've got are in bounds, and how would they work and fit in your system? Can you understand trends? All of these things that they're going to want to know and see very, very quickly as operators. So as soon as a pass is done, you've then got an hour and a half to figure out what you want to do next, but you need the tools to analyze that with, rather than perhaps doing what I'm used to doing, which is messing around with hex and then writing little custom decoders on the fly. Okay. It will have a beacon on it. It is a fairly loud beacon. But what you'll be able to see is it will be modulated based on the battery. So in particular, the things that you want to take care of is very quick identifiers as to what your battery state is, and we can modulate the beacon so that our communications really doesn't become a sort of downfall for the particular system. It's very, very safe. What will the beacon have in it? I hear you all ponder. A lot of things. It kind of comes in a number of different flavors because all of these things are configurable through an array on the onboard computer. But we've had some recommendations that we've said that the Algerians should start to look at. The ones in bold, which will come down in what we call our critical or safe mode beacon, which will always be battery health, currents, software versions, uptimes, traffic counters as well, RSSIs, Dopplers, all of these different pieces, as well as perhaps your battery states from temperatures as well. So we can get something quite small down. The beacon is very, very short, 3-4 seconds. But if we want to we've got quick commands that can put us into our nominal beacon mode. And the nominal beacon mode then gets you all the other stuff that isn't in bold. So things like our reset counters, our estimation modes, the solar panel pieces, and amateur radio text messages. So there is a message in there for those of you that wanted to pick that up in raw ASCII. Yeah, I think that's roughly it, but they can configure it themselves. So if they wanted to, for instance, look at magnetometry in a fairly serious way, they can do. This larger beacon lasts just under 10 seconds as well. I've got to kind of bash through that, so there's actually some time for some questions. But we've actually generated a document which is going through the process of review with all of our partners, with ALSAT, with the payload providers, with the UK Space Agency, so that we can get the word out, and hopefully you'll help get the word out as well. This is our downlink frequency, be on 437 650, and it is an FSK G3RUH system like we had with Strand 1. And as usual, you can send in your KISS files. They pop up straight away in our mission control client, which is very wonderful. We did that before. And ASAL also have their own email as well that they'd like you to know should you want to get in touch with them as well. And that's the end of our second presentation for today. Happy to take questions.
Right, thank you very much, Chris. I think you're working faster than 9K6 sometimes. Have we got any questions from the floor, please?
Yeah.
The first presentation. Oh, sorry.
I can repeat the question if it helps.
Right. So, thinking about the first presentation, obviously the debris you're targeting right now is sort of big chunks of stuff, I would say, looking at the technologies. But obviously there's a lot of almost microscopic stuff out there that is just as dangerous because it's travelling so fast. It's like a bullet, isn't it?
Yes.
Are you looking forward to using other methods of picking that up? I don't know what, electrostatic, something. Is there any research going on into that?
Yeah, so there's a heck of a lot of research going on in understanding, kind of, first of all, identifying what objects you're going to need to take kind of out of the system to have the biggest impact. So there's all sorts of studies to say whether or not you're taking NVSAT, rocket bodies, things that actually are, we know to be the risks. So the myth is that obviously it's everyone launching CubeSats. The reality is it's a piece of rocket bodies and old spacecraft that have propellant in them that are then going pop and then creating these things. So there's a bit of that, but with regards to the sort of small pieces, it's about tracking. How do you know where they are? And the problem is that some of those systems that we need to track smaller objects aren't coming online for a number of years. So I know the US and the guys out of JSPOC with their radar systems are working on things to go centimetre-ish, but obviously our smallest is about 10 centimetres, which then limits the sort of thing that you can actually really be worried about. So yes, we're almost certain that they're there, but it's a question of then how do you identify them, how do you know where they are, so that you can then go and do something about it. And I think that's part of the big crux of it all at the moment.
Okay, thank you, Anne. Any others?
First presentation, deorbiting. Can you predict the deorbiting path, or
yes.
Is that a surprising act?
Yeah. So I was prepared for this. Yeah. So one of the things that we are doing actively with our partners at Airbus and SSTL is understanding what the debris risks are going to be, where they're going to land, what the drag effects are, all of these different pieces. When it burns up, it will burn up. The key thing here is it meets the deorbiting recommendations of 25 years. That's kind of all you can really say about these things. There's one from Graham.
Chris, I think I remember that the LightSail 1 mission was not entirely successful in unfurling their sail. Do you know what went wrong? You don't have to say if you're not allowed to, but have you taken countermeasures for your mission?
Yes and yes. We'll talk later.
Chris, I haven't actually got a question for you, but I've got a question for James, who's in the room, G3RUH, who was mentioned on the screen there. I won't ask him how long ago G3RUH modulation scheme was invented, but it was some time back. I wonder whether he's got any ideas as to what we should really be using now. I mean, the whole world, pretty well, of CubeSats, great exaggeration. An awful lot of CubeSats are still using what James developed some time back. I wonder whether in the room here we could ask James what he thinks we should be doing now. It can't still be the right thing or the best thing, can it?
Where's James? Yeah. There he is.
First answer is 1988. The second answer is I need notice of the question.
Likewise, yeah.
But your comment about out-of-datedness is probably valid. That will do.
The key reason why we do use it, of course, is that there's still readily available amateur radio equipment that is highly compatible with these modes. And of course, when we're using amateur frequencies, it's important that as universities and researchers that we give something back. Yes, you can put various different grades of forward error correction and other systems on these things, and how you frame those things is obviously going to be very mission specific. But in this particular case, if we wanted to have the reach that we would like, we even need to develop and give out new systems and new standards, which in today's world there's an XKCD cartoon about standards, which I'm sure perhaps many of you are familiar with, which is, yeah, we need this new standard to do this thing, and it'll be grand, unifying, blah, blah, blah. Of course, all you've done is just created another standard. No?
Okay, I think that's it. I've just got one quick one.
Sure.
Your harpoon, death spear.
Simple
thing, it goes out.
Yes.
What do you do about the reaction to it going out? How's that?
So the reaction, are you talking about the actual kinematics?
How's that taken care of, yeah?
Yeah, so that's actually one of the things that we need to be measuring, period. So we understand that the mode, so when we push out the actual plate itself, there will be momentum and forces imposed and torques imposed on the system, and you need to just be able to allow that to kind of rotate. They're not measuring to be large from our particular modelling, but yeah, I mean you're going to get a torque. So any deployment mechanism, anything that wants to move in your spacecraft is going to develop the torques. It's going to change your moments of inertia, change your centres of masses and pressures, and they can happen. It just depends on really the scales. So with a larger spacecraft, obviously our moments of inertia are much larger. It makes it easier for us to then do those controls so that when forces do act on them, it's much less. Yeah. And I think that's the key thing there. If we were starting from a CubeSat, they have very, very low moments of inertia, highly low. And that's part of the problem in some of the attitude control that we've seen perhaps with CubeSats.
Yeah. Okay, thank you. I'd like to show appreciation again.
Thank you.
Right, we just bear with us for the next presentation.
Who's next?